Okay, back to 3PN4 Chapter 8. We're going to introduce the bipolar junction transistor. This obviously is an extremely important step in the world of electronics. It happened in the 1950s at Bell Labs. And the invention of the bipolar junction transistor, which I'm going to describe, actually happened a little bit unintentionally, because the intention was to invent a different kind of transistor, more similar to a field effect transistor. And the field effect transistor ended up in the form of a MOSFET, a metal oxide semiconductor field effect transistor, which has become the dominant type of transistor in microelectronics today. We're not covering the MOSFET in this course. It's covered in materials in EngFS 4MD3, at least when I teach it. But in this course, we're going to cover a transistor which is called the bipolar junction transistor, which, as I said, was accidentally discovered at Bell Labs. And at the first, they didn't really understand how it worked. But once they did, it became the transistor of the 1950s, 60s, 70s, 80s. And it's still in heavy use today. So it's used in many specialty applications, power applications, switching applications, analog applications. And in many cases, it's combined with MOS transistors to create what's called a bi-MOS technology, which is a combination of bipolar and metal oxide semiconductor field effect transistors in one integrated circuit. So to begin with, how does BJT or bipolar junction transistor work? Well, fortunately, the background you have in the PN junction and the solar cell and the LED is really sufficient to understand this quite readily. So let's start looking at a reverse biased PN junction. So we're going to connect this PN junction in reverse bias, which means that our IV characteristic, which looks like this, is going to be, let's say, operating right there. So this is our operating point in the IV characteristic of a diode. And with this reverse bias, what's going on inside the energy band diagram is that we have, in the P side, a very small number of electrons that trickles down, and a very small number of holes that trickles down, and that represents the reverse saturation current. Now, on the other hand, when we go into forward bias, so let's now think about a forward bias PN junction. We have a very nice model for forward bias, where on the P side, the excess electron concentration, delta N sub P, builds up due to the forward bias, and correspondingly delta P sub N builds up in forward bias on the N side. So here's the challenge. If we want to change the reverse saturation current, which is usually really small, we can do it with light. In a solar cell, light causes electron hole pair generation, which increases that reverse saturation current. But we can also do it electrically, and that's what you do in a bipolar junction transistor, is you electrically increase the reverse saturation current, and you do that by increasing the carrier concentration in either the conduction band or in the valence band, so that you get a lot more carriers during reverse bias, and the increased number of carriers is controllable. So if you can control that increased number of carriers, then you can increase that reverse saturation current. Well, the clue as to how to do that is in this forward bias junction, because we are in fact increasing the number of carriers on each side of this junction, and specifically the increased number of minority carriers. We're controlling the minority carrier concentration in the p side with these electrons and in the n side with these holes. So the question is, could we somehow take the properties of a forward bias junction in which you vary the minority carrier concentrations and couple that forward bias junction to a reverse bias junction, which could then have a varying reverse saturation current? And the answer is yes. So I'm going to draw the configuration as it exists in the textbook, and you'll see that we're going to end up with a forward bias junction as well as a reverse bias junction. So this is figure 8.3. And we're drawing here a PNP transistor, which is going to have a forward bias junction. So this junction here is going to be forward biased, and that junction will be reverse biased. So to achieve that, we're going to forward bias this junction with a voltage source that has its positive terminal connected to the P region. And then we're going to add a reverse bias with a second voltage source, which has its negative voltage connecting to that P region. Now, how can this work? Well, this forward biased PN junction causes holes from the P plus, the heavily doped P side, to be injected into the N region. And that injection of holes looks something like this. This is X sub N. So now I'm looking at the penetration depth within this N region, and this is delta P sub N, the injection of holes from this P plus region into the N region. Those excess holes will now show up at the reverse bias junction here. The second junction, being reverse bias, will detect that excess number of holes, provided that the second junction is close enough to the first junction. If the second junction is way far out, the holes will have recombined before they can reach the second junction. But if the second junction is spaced away from the first junction by well over one diffusion length, remember that the diffusion length is a measure of the decay distance of that minority carrier concentration. As long as we can keep our second junction well within one diffusion length of the carriers in this N region, we can have access to those carriers across this reverse bias junction. And what will happen, if you look at an energy band diagram, is that the holes that we've injected, these excess holes in this N region, will show up here, and they can then drift across due to the electric field in the NP region in reverse bias. So this is the reverse biased NP junction. And the holes here arrived from forward biased PN junction. Okay, so you have holes arriving from a forward biased PN junction. Those holes travel to the right. As soon as they experience this electric field, they will drift towards the P region. So what you can do is you can apply a voltage here which controls the excess hole concentration in this region, and you can control that excess hole concentration with a rather small change in the voltage here. You're only changing this voltage from, let's say, 0 up to about 0.6, 0.7 volts in silicon as you go from 0 bias up to a strong forward bias. So only a fraction of a volt of variation in this voltage causes many orders of magnitude change in the excess minority carrier concentration in this region, which can then cause many orders of magnitude change in the electric current flowing through this reverse bias junction, which can then cause many volts to show up across this resistor, because it all depends on the voltage you put here. You could put 100 volts here, and now you can control the current through this resistor and end up with up to 100 volts, or between perhaps 0 and almost 100 volts across this resistor, and you've only changed this voltage by a fraction of a volt. So you've created a voltage amplifier, and in fact we'll see soon that you can also create a current amplifier by this device structure. So it's very ingenious, and it relies on the excess carrier concentrations we can generate as minority carriers in semiconductors. Now we call these different terminals names. We call this terminal the emitter. We call this terminal the collector, and we call this terminal the base. And historically, the reason for the name emitter is quite sensible, because we're emitting carriers from the side. The name collector is very sensible because we're collecting the carriers that sweep across this reverse bias junction. But the name base doesn't make any sense at all from a performance point of view. And the reason for the name base arose from the original Bell Labs invention. They had in the experiment, they had a slab of germanium. Germanium was a semiconductor which was actually predated silicon. So you can make a very good germanium bipolar junction transistor. It doesn't quite have the ability to tolerate higher ambient temperatures, and germanium is much more expensive than silicon, so germanium quickly gave way to silicon as the transistor developed and matured. But the early transistors were all made of germanium, and at Bell Labs they created a P region on this germanium. So the germanium was actually N-type. So in order to create the collector and the emitter, they put a blob of indium, which is a group 3 metal, on one side, and another blob of indium on the other side. And they connected 2 wires to those 2 blobs of indium to form the emitter and the collector. And this material, the germanium slab, was connected to a platform to hold the whole thing up. And so as a result, this became known as the base because the device was supported by that sheet of germanium, which became the base. And the electrode in the base was connected to that block of germanium. So from a performance point of view, the word base is meaningless, but it's stuck with us till this day. Now, in order to optimize certain things in this transistor, let's just go back to a forward bias junction. If we look at that forward bias junction, and you forward bias it, you will get excess minority electrons in the P side. You'll get excess minority holes in the N side. Now, the reason for making this a P plus N junction is because we want to really have most of the current flowing through this forward bias junction. We want most of that current to be due to holes, because it's the holes we're trying to inject into the base so that they can then end up at the collector. The electrons that we inject from the base into the emitter material are not useful to us. In fact, they represent a waste of current because we don't want to have a higher current flow into our emitter than necessary. So that's the reason for the P plus N doping. By having a couple of orders of magnitude higher P doping than N doping, we can restrict this unwanted current to about 1% or less of the total emitter current. Now, the other interesting thing is I mentioned that a transistor can actually give you current amplification, not just voltage amplification. And to provide current amplification, what we would do is think about controlling the transistor through the base. So imagine if instead of controlling the voltage on the emitter, imagine that we control the voltage on the base with an appropriate adjustable voltage supply. So here's an adjustable voltage. It'll give us a forward bias across this emitter base junction. And to do that, I'm applying a negative voltage to the base, a varying negative voltage. How much actual current is flowing into the space? Well, actually, the current is actually flowing out of the base because of the polarity of this voltage. So instead of talking about current for a minute, let's just talk about where the holes are going. We're injecting holes into the base. Those holes become minority carriers in the base. Those minority carriers might then continue flowing through to the collector, because as holes they can continue into the collector, in which case they don't contribute to base current. There's no base current due to the carriers that flow through the base from the emitter to the collector. They don't flow in and out of the wire connecting to the base voltage. On the other hand, some of these holes could recombine. So you could have recombination processes taking place as those holes pass through the base. And if a hole recombines, it must draw in an electron. So an electron must actually flow into the base to recombine with any hole that doesn't make it across. And you can see the hole concentration in the base looks like that. That hole concentration, if the base width is a certain amount, W, is still going to suffer a certain loss in concentration. So that loss in hole concentration through the base will represent holes that recombine within the base, and every time one of those holes recombines, it causes an electron to flow into the base. So as a result of that, the current flowing into the base would flow this way. And that base current, of course, by convention, flows in the direction opposite to the electrons entering the base. And the majority of the holes will flow through into the collector. So the one source of base current is a recombination of minority carriers in the base, and that's likely to be the dominant source of base current. Another source of base current is, remember that we try to minimize the number of electrons which are injected from the base into the emitter. Every time an electron is injected from the base into the emitter, it requires an electron to enter the base, which will eventually get injected into the emitter. So we'd like to minimize the injection of electrons into the emitter, and again, we achieve that by having a light doping in the base and a heavy doping in the emitter to cause as much of an imbalance as possible in the hole versus the electron current. So we're now ready to start analyzing the bipolar junction transistor in more detail. We're going to use all the modeling tricks we've learned in the past, the diffusion equation and the diffusion current density and so on, to create a model. So you'll find this model quite interesting, and you'll find it's quite a good review of the concepts that you've learned in chapter 3. So to start out, we will put a coordinate system together. That's going to be the emitter. This is going to be the base. And we're really going to focus on what happens inside the base. That's where all the really important physics is in the bipolar junction transistor. And the emitter is going to end just away from that because there's some kind of depletion region between the emitter and the base. And there's another depletion region between the base and the collector. I've drawn this depletion region here to be wider than this depletion region, because this would normally be reverse biased, which would increase the width compared to this depletion region, which would typically be forward biased or have a very small bias on it, which would cause it to be narrow. In fact, in a forward biased diode, I shouldn't really be thinking of a depletion region, because the forward biased condition will decrease the effective width of a depletion region. So what we can do now is plot on the y-axis delta P sub n of xn. So what we're trying to find is the excess hole concentration in the base as a function of xn, which is the coordinate which goes between 0 and WB in the base. So the first question is, what are the boundary conditions? What is the excess hole concentration at the base emitter junction? So we know that expression because delta P sub n at xn equals 0 equals P sub n e to the qv be over kt minus 1. So we're simply using the diode model for the emitter-base junction. In the diode model, the excess hole concentration is exactly as I've written here. All I've done is now call this voltage VBE, the base emitter voltage. On the other hand, in the transistor, we're going to make an approximation. We're going to approximate this as P sub n e to the q VBE over kt. And this approximation is valid provided we're not dealing with a very, very weak forward bias. So we're just going to consider forward biases that are reasonably significant. Now, the other boundary condition on this side is that delta P sub n at x n equals WB is P sub n e to the q v CE over kt minus 1. So we're now going to consider the collector emitter voltage, the collector base voltage. I'm sorry, this should be a V, not. So we're considering the collector base voltage to look at the collector base junction. Now remember that that junction is reverse biased, and that reverse bias means that this is a relatively large negative number, and we're going to therefore assume that this term is essentially 0. So this is approximately equal to minus P sub n. In other words, it's very, very small, because P sub n is the equilibrium minority carrier concentration in the base. Base is n-type material, P sub n is the minority hole concentration in the base. Well, we're going to further approximate that to 0 because it's so insignificant, and it just means the equations that we continue with will be easier to write down. So we can now put together the diffusion equation because we're going to make the assumption that the base itself does not have electric fields in it. We wouldn't expect an electric field in the base because the electric fields would all be in the depletion regions. The base would have current flow due to diffusion, just like in a regular p-n junction. We only looked at diffusion outside of the depletion region. So once again, in the transistor, we're going to assume that diffusion is the only flow process. And so this flow process in the base will be represented by the diffusion equation, and we are quite familiar with the general solution to a diffusion equation. So those are the two terms we would have in that diffusion equation. And we can apply the boundary conditions to that diffusion equation. So First of all, at x sub n equals 0, the result is just C1 plus C2 because x sub n equals 0. So those two exponential functions become 1, and you just get C1 plus C2. And if you go to WB, you get that result. So we have two equations. We have this equation and we have this equation. And we can solve those two equations for the two unknowns we have, namely C1 and C2. So if you solve for the two variables, C1 becomes delta P sub n at x sub n equals 0 times e to the WB over LP divided by e to the WB over LP minus e to the minus WB over LP. Okay, so we've used this equation, which had delta P sub n at x sub n equals 0, and we've used the other equation to get this result. So you should make sure you agree with that result for solving those two equations. That's for C1, and then for C2, the result is quite similar. You get that result. So now things get a bit messy because we have to now substitute our values for C1 and C2, and we have to substitute them back into this diffusion equation, and then we can get the general solution for the carrier concentration within the base. And I'm going to simply give you the result. You can do it really easily for yourself, and I'd suggest you do that so that you know I'm not trying to fool you. So we've got delta P sub n of xn equals delta P sub n of xn equals 0, e to the WB over LP, e to the minus WB over LP, I'm sorry, e to the minus xn minus e to the minus WB over LP, e to the xn over LP divided by e to the WB over LP minus e to the minus WB over LP. So that becomes the minority carrier concentration in the base. And what's more meaningful than this equation is to sketch it. So it'll look something like this. So it starts out on the left-hand side, which is when x sub n equals 0, at delta P sub n at xn equals 0. And it ends up on the right-hand side at WB. one thing that you'll notice if you sketch this is that it's a slightly concave shape compared to a straight line. So that dotted line is a straight line. This shape is slightly concave. And that becomes a very important aspect of that curve. Now, in order to make use of this carrier concentration, we'd like to calculate the current flow. We want to know how much current is flowing into the base at x sub n equals 0, and we want to know how much current is flowing out of the base at x sub n equals wb. Because the current flowing into the base and the current flowing out of the base represents the surviving current, or let's say the surviving current is the output current divided by the input current, but the remaining current, which would be the input current minus the output current, would be the current loss, which would contribute to base current, and we're trying to minimize base current. So as we did in the p-n junction diode, we can calculate currents by taking the slope of this line and putting that slope into the expression for diffusion current. And we can put the slope there into the expression for diffusion current, and we can put the slope there into the expression for diffusion current. So the expression for diffusion current, IP of xn equals q a dp d delta p of xn by dxn. So this curve is delta p of xn. So we're going to take the slope of that curve, and here A is the junction area, and then we're going to calculate the current. Well, we know that IP of 0